Hello, my name is Zachary Kotaros. Today I am presenting my multi-component mass balance on cooking pasta. This is my experimental project for CHBE 101. Um, my primary objective for this experiment was to apply the law of conservation of mass to model and solve an open, unsteady state batch process. The core concept that I'm covering is the total mass entering our system must balance with the total mass leaving, which is also just total mass in equals total mass out. Um, the pictures above are this is my cooking pot at 1252 grams. The second picture is my glass bowl one with my dry pasta, and the pasta weighs 156 grams, and the mass of the glass bowl one is 931 grams. The third picture right here is the pot with the water, and the balance was zeroed out. So this is just the mass of the water at 1,792 grams. And then the fourth picture is just my plate, and the plate is 899 grams. This is my experimental methods and data analysis. I brought the water in the pot to a rigorous boil and started a 8-minute timer for cooking. And I established 2 points at which I would collect data, one at 4 minutes, where I would take the temperature of the rising vapor directly above the liquid, which resulted to be 134.6 degrees Fahrenheit, or also 57 degrees Celsius. And then at 6 minutes, I held the cover, the pot lid, over the plate that is in this picture right here, at 6 minutes, and allowed the water to fall onto the plate, which resulted to be about 2 grams. So over the 8 minutes, I strained the pasta and determined that the mass of the water and the mass of bowl 2 weighed about 2,776 grams, which is seen right here and right here in the picture. And I used the mass of bowl number 2, which was 1,518 grams, to get a total weight of 1,260 grams of cooked pasta water. And then this bottom picture shows the mass of just the cooked pasta at 509 grams. I used the amount of the mass of water, which was 1,792 grams, and subtracted that from the mass of the cooked water to get 532 grams, which showed me the mass of the steam. And this bottom calculation shows the mass of water absorbed by pasta. So I took the mass of 532 grams, which is the mass of steam, and subtracted it from the mass of dry pasta, shown in this picture, to get 376 grams, which shows the amount of water that was absorbed by the pasta during the cooking of 8 minutes. This is my mass balance slide, where delta M steam total equals inputs minus outputs. And delta M steam total expanded equals the mass of the dry pasta plus the mass of the water put in initially, and you subtract that from the mass of the cooked pasta plus the mass of the liquid, or the water, after the 8-minute period of cooking. And then this is the numbers plugged in. So this is the mass of the dry pasta, mass of water put in, and then subtracting the mass of the cooked pasta and the mass of the cooked water. So the amount of steam lost was 156 grams, because this measures the amount of mass put in, and this measures the amount of mass out, and you subtract them. This is my mole fraction and flow rate slide, where the mass flow rate of steam, calculated here, of 156 grams is divided by 480-second duration, which is the 8-minute period of boiling the pasta, and I got a 0.325 grams per second. And then I took the molar flow rate, or the mass flow rate of water condensed of the 2 grams collected from the pot lid, divided it by 60 seconds to get the 0.0333 grams per second. And that was converted into a molar flow rate where I took the grams per second and divided it by the molar mass of water to get 0.00185 moles per second. To continue using the Antoine equation for water, I've used the measured temperature above water at the 4-minute period during the 8 minutes of boiling to be 134.6 degrees Fahrenheit and converted that to Celsius, which is 57 degrees Celsius. Plugging that into the equation, which is log 10 P star water and everything that follows over here. Solving, the specific vapor pressure of water at that temperature is 129.54 millimeters of mercury. Then over here, to find the gas phase mole fraction of water, I take the vapor pressure of water and divide it by the total pressure, which is atmospheric pressure, which is 1 atm equals 760 millimeters of mercury. So I take the specific, like I said, divide it, get 0.17, which is the mole fraction of water vapor leaving the pot. So yeah, down here explaining vapor pressure, 17% vapor pressure, or water vapor, and 83% is air. And I said error in measurement because when trying to take this measurement, I had to take the lid off, and I was struggling to find a way to contain all the steam with also measuring the temperature at 4 minutes. So I had to take the lid off, and that also impacts my condensation amount right here, because I lose water that way. And also it makes this data unreliable because the vapor isn't contained and it's allowed to go. That's also why there's an 83% of air. And then the total vapor flow rate is the mole flow rate of water over the mole fraction of water, which is just taking the molar flow rate here, taking the mole fraction right here to get the total vapor flow rate of 0.0109 moles per second. And then so this is a picture of the pasta that I used to cook with some sauce that my brother made, and this is it after. I also had an issue with the bubbles formed from the boiling coming out of the lid, and so I lost water that way. And I was trying to put ice cubes in it to help with the water, but at the time I should have just turned down the temperature. So in that way I also lost water that could have been condensed. And also this is the end of my experimental project, and thank you for watching.